Okay, we're looking at chapter 16 today, which deals with thermodynamics. Now this actually blows up into a class all by itself in later chemistry. You'll have, if you're a chemistry major, the next class that you have that deals with this stuff is physical chemistry, and it will bring in some calculus into this stuff. We're going to avoid all the calculus, but what makes this complex is we're starting to try to understand what the heck a spontaneous reaction actually is. Alright, technically speaking, a spontaneous reaction is something that will go forward even when it seems like it shouldn't. And the example on this page is a really neat one that we can actually do in any chemistry lab. So we mix two salts. It's barium hydroxide. The water's just there because this is a crystal. It absorbs water. It forms a nice little solid crystal. And ammonium nitrate's also a solid. But if I take these two solids and mix them, just that physical mixing, that solid gets cold. And it's actually cold enough that, kind of think magic trick, we'll put a little spot of water on that board and we will stir this up, and then we just move the beaker on top of that water. It is actually cold enough that it will actually freeze that water very, very rapidly, and you can pick up the board because it's actually frozen. Alright. Neat experience, neat experiment. Looks really cool, but really it's weird though, because you would think stirring things, if anything, it should make things hotter because of friction. But this one, just mixing those two solids together, it gets cold. Alright, so we're going to try to understand what the heck's going on here, and more importantly, what makes a reaction spontaneous even when it seems like it goes against what you would think should happen. Alright, so let's talk about where we got to this point to understand it. So way back when we first introduced our whole idea of energy, we introduced this nice little equation, Q plus W, which is resulting in from the energy of a reaction or any change. But what we actually said was a chemical reaction, when it releases heat, it can be released as heat or work. And that technically was just the first law of thermodynamics. Problem with the first law of thermodynamics is it doesn't talk about a direction or which way is favorable. And yet we do know that's the case in most chemical reactions, and actually most reactions in general. It's very easy to watch ice melt, very challenging to get it to freeze without like a refrigerator. So the direction is not covered in that delta E equals Q plus W. Alright, so let's talk about how we're going to make sense of this. So let's break it down to something really simple. A true spontaneous reaction that seems like a no-brainer that it would happen. So we have two glass containers that are sealed, and they are connected to one another, but we have a valve between the two. Now we're going to fill up one side with a gas. Doesn't matter what it is, just a gas. And we're going to open that container. It makes perfect sense that eventually, and it would depend on the size of the hole, but eventually you'd have equally distributed amounts of gas. Number of gas molecules on either side would be the same. And it would happen just because you opened the valve. You wouldn't actually have to do anything else. Physics or Mother Nature or magic would take care of everything that you see going on here. Well, technically that's a spontaneous reaction. And a non-spontaneous reaction would be trying to undo it by just twisting that valve. And obviously, once you twist that valve back closed, you're not going to get it to go all the way back, all the gas molecules all the way to one side, just because they want to. The spontaneous reaction is that fully expanding of the area. Alright, we see the same thing with heat as well. And what I mean by that, what I'm looking at here is we'll call these two blocks of metal. I got one block of metal that's hot. I got one block of the metal that's not as hot. If I put them next to each other, as in contact, the hot one will heat up the cold one. That heat transfers. Well, heat is a spontaneous flow. It's very difficult to stop it. About the only way we can actually stop heat from flowing is to truly isolate it, which is what the insulation does in our houses, styrofoam cups. It creates a dead air space. So if there's nothing to contact the two blocks, they don't transfer. But heat flow itself is spontaneous, and there's nothing we can do to stop it. Alright, so where we get to where we are now is introduced by these two gentlemen. On the left here is this guy named Carnot, and he was kind of interesting. He was looking at these hot blocks. So prior to him, and with possible exception his father, most scientists were saying that heat was a physical object. Newton thought it was an object. A lot of other scientists thought it was an object. And what they would have said was this hot block had more heat particles in it, and when they came in contact, the heat particles transferred. And that actually makes sense, because if you weren't in contact, the heat couldn't transfer. So they thought they were physical objects. Well, Carnot thinks it's not physical objects, it's something, the heat is somehow related to how those objects are moving. On the right here is this guy Clausius. He's doing the same thing, but he's starting to understand about the size of the particles we're talking about and realizes we're dealing with really, really, really large numbers, as in the number of atoms in like that block that are moving. But these two get us started, and they give us this word entropy, which is going to be a measure of chaos or disorder. All right, what I mean by that, it is a exponential scale number. It's a calculation of microstates. All right, so what is a microstate? Well, what we're going to do to explain a microstate, we're going to look at down here at this little set of boxes down here, and all we're looking at this box, this thing is, we're going to look at how we can arrange 4 different marbles in 2 separate boxes. All right, what I mean by that, we could put all 4 on one side. We could put 3 in one side and 1 on the other, and we can do that multiple different ways. We could put 2 and 2, and we can do that multiple different ways. Then we could do 1 and 3, multiple different ways, and then 1 more where it's just 4 on one side. So we're showing all the possible ways we could arrange those 4 marbles in these 2 boxes. Well, what we see is, what these guys were saying is the sheer number of microstates is what creates the disorder. The reactions, the heat, wants to go to a point where there's more microstates, or more chaos, more movement, more area. But we are actually seeing that this is a nice little bell curve where pretty much we're seeing things in averages. And we see that with microstates in general, or entropy in general. Alright, so even though it's a weird mathematical thing, how do we relate it to real things? Well, we can see an entropy increase just by changing temperature and physical state. And that's how we're actually going to look at entropy in general. When we think about it, we don't want to think about the sheer number of microstates, because that's an absurdly huge number if we're dealing with a mole's worth of atoms. Entropy is a measure of disorder or chaos. So we want to think of it in that sense. What causes the particles to move and give us that more chaos or disorder? And the 2 main things that actually do drive it are our temperature and our physical state. And what I mean by that 2 main things, let's think about that. So if we have physical states, solid, liquid, and gas, solids don't move hardly at all. They kind of vibrate in spaces. They're like the students in a classroom. You're stuck in your seats and you can't move around. All right, liquid is more like think still classroom, but it's now the recess, inside recess, so you're able to move around some, but you're still confined to that small classroom. And here, gases, that's chaos. That's the end of the school day. You're able to go anywhere you want. All right, but that chaos, that disorder, is what we're seeing increase. We're actually getting more movement, more degrees of freedom, more entropy as we go from solid, liquid to gas. And same thing kind of happens with temperature. Go back to when we first introduced our gas laws, we talked about the speed of the molecules was, the average speed was directly related to the temperature. And you increase the temperature, you increase the average speed. Well, since entropy is a measure of movement or disorder, faster movement would be more disorder. Alright, so our 2 main things that drive it really are phases. As in, if I give a chemical reaction that just looks like this, we have liquid water going to gaseous state water, or gas. My G looked like an S. That's not a good thing to mess up on. Not on this. Alright, but that chemical reaction showing water going from liquid to gas would definitely be an increase of entropy, simply because we're going to get more disorder by becoming a gas phase. All right, the next two are almost the same thing. We're talking about dissolving stuff into dissolving a solid or liquid into a liquid, and dissolving a gas into a liquid. All right, let's look at a couple examples to see what we're talking about here. So when I mix a solid into a liquid, that should be expected to be an increase of entropy, because let's think about this. I have sodium chloride as a solid. It's limited in its motion to just those vibrations because it's stuck in that crystal form. But if I were to dissolve it and actually give individual sodium ions and chlorine ions floating around in there, they now have that full area of movement that the liquid provided them. So the sodium and chloride can more spontaneously move around. That's an increase of entropy. Same thing happens when two liquids mix. Now this one's a little bit easier to see if we think about it more like in a beaker or a graduated cylinder. Alright, so if I put 10 milliliters of ethanol into a container, and then right on top of it I put 10 milliliters of water, technically that now 10 milliliters of ethanol has more volume to move in, because they're going to mix, they're able to interact with each other, and they are going to not separate. So we're going to have a entirely larger volume for those individual molecules to move around in. So anytime solutions dissolve into each other or mix, you get an increase of entropy. Now the one that does go down is dissolving of a gas into a liquid. But this kind of makes sense if we stop and think about the disorder here, because oxygen gas, like in this picture, has that freedom of movement above that container where it's only actually interacting with other oxygen molecules or gas molecules, but they're going to bounce around without too much interaction. But if that oxygen gets dissolved into the water, now it has much more limited motion, so less disorder. So dissolving a gas actually decreases this disorder. All right, so, but these are actually going down in priority. They don't make as big of a deal as the temperature and the physical state. All right, and the last one is atomic size, or the complexity of a molecule. Now, atomic size can be as simple as this. If we wanted to compare CH4 to CF4, should be reasonable to expect that CF4 would have more entropy, simply because it's a bigger molecule. It's heavier, and therefore it's going to actually have a little bit more disorder in its motions. All right, the complexity is a weird one, though. This makes sense if we look at a molecule or some examples. So what we have here is some various different molecules made out of just nitrogens and oxygens, and we're relating entropy to how the molecule vibrates. And that's what these little arrows are representing. We view bonds as kind of like springs. Some are stiffer than others. Some are stronger than others. So we have some that bounce a lot more, and we have some that vibrate a lot more. But technically speaking, the more bonds you have, or the more springs you have in a molecule, the more vibrations you're allowed to have. So as you get more and more complex, those vibrations translate to more internal motion. But what's weird is, if you'd done these and just said molecular weight, you would have said the smallest does have the lowest entropy, just because it weighs less. So generally speaking, we can get by in a lot of cases just by looking at the actual molecular weight and deciding if it has more or less entropy. Alright, let's try to apply these to some examples. Okay, on that first one we have 1 mole of SO2 gas versus 1 mole of SO3 gas. Alright, since it's 1 mole of each, and that's the only thing that's really changing is the formula, SO2 versus SO3, because they're both gases, we're going to go with the bigger one, because that's more molecular complexity. Alright, B, I have 1 mole of CO2 solid versus 1 mole of CO2 gas. So it's 1 mole and 1 mole, both the same molecular formula. So we're going to focus on the fact that that's a gas. Alright, the next one, 3 moles of oxygen, O2, or 2 moles of ozone, O3. Alright, here's an interesting one. Had it just been O2 and O3, we would go with the O3 because the ozone is more molecularly complex. But here's a weird one. It's 2 moles versus 3 moles. That's just flat out more participants. Alright, the next one, 1 mole of potassium bromide solid versus 1 mole of potassium bromide aqueous. As long as it dissolves, it now has more area to move around in. And now we have water at 2 degrees Celsius or water at 23 degrees Celsius. Warmer. And then the final one, 1 mole of CF4 or 1 mole of CCl4. Heavier. So we got molecular weight that decided this one, temperature here, solid is being dissolved, more molecules, gas, and this would be back to molecular weight. Alright, now that's how we go about predicting it. We're going to see we're not always able to predict it. Sometimes we can, sometimes we can't. We're going to look at a couple different ways to actually predict it, and more importantly, how we're going to calculate if we can't. Alright, so turns out we can get the entropy of a system from tabulated values. You might recognize this equation. We had something similar to that back in, I think it was chapter 5 or 6 in Chem 1, dealing with delta H's. We could actually look up in the some tables in the back of your book, some H's for individual reagents, like products and reactants, and did a nice little subtraction. Well, turns out that section of the book that had those delta H's, like we used in Chem 1, also had S's, entropies. And we're going to do the exact same type of thing we did before. We're going to add them up, products minus reactants, and solve for the entropy in some cases. Alright, now that's going to give us the delta S of the system, which is the reaction. So I'm also going to put over here delta S of the system. Now, interesting, when a reaction occurs, if there's heat given off, like a delta H, that heat goes out into the surroundings and causes disorder. So there is a delta S of the surroundings, but it really almost never, it doesn't have anything to do with the delta S of the reaction. This is just the chaos in the container. That's how the molecules are moving around more more excitedly or more rapidly, or just flat out more disorder. The disorder that's caused in the universe or out in the surroundings is because the heat of the reaction goes out there and heats them up and causes them to move more. So we have two different delta S's we sometimes calculate. Delta S of the system, using tabulated values in the back of the book of the delta S's. To get the delta S's of the surroundings, we're going to get them from the delta H of the system. Alright, why do we need both? We're going to see why that is. Let's get them though. Let's get them first. Alright, so let's practice this with some values from the back of the book. And we're going to get a delta S of each of these reactions. Now, first thing we're going to do is try to predict if we think it's a positive value or a negative value. Not an actual value, just if it's positive or negative. Now that first one, we can kind of do that, because as one of my reactants, I have a gas. And I don't anymore. Well, taking a gas away, all that disorder, that's likely to cause us to go negative on our delta S's. Anytime we have gases that go away, you end up typically with an entropy of a negative value. Now, if you make gases, it's kind of a positive. And down here in this bottom one, I really can't make that call because I have gases on both sides. So on this one, I'm just going to actually put a question mark. Now, something else we have to watch out with. How this question is worded right now, there isn't one correct answer. And it's mainly because we don't have a balanced chemical equation to start out with. So the very first thing I'm going to do is actually balance it. I'm going to need 2 sodiums to get those 2 sodiums. I got 1 carbon, and right now I have 2, 3, 4 oxygens. 1, 2, 3, 4 oxygens and 2 hydrogens. Alright, that 2 balanced it. Alright, so if I want to get the delta S for this particular reaction, I'm going to add up all the delta S's of our products. So I have 1 sodium carbonate, and I have 1 water. That would be my only products. And I'm going to subtract the delta S's of my reactants. I have 2 sodium hydroxides and 1 delta S, or CO2. And then, if I want to actually get this, I just fire up my calculator. So 139 plus 69.9 minus 2 times 64.5 and also minus 213.7. And we get a delta S of negative 133.8. And units for S's are joules, moles, and Kelvin. Alright, we had predicted negative. We got negative. Alright, the second one we couldn't make that prediction. We do need to balance this. So I have... Actually, I'm going to do the oxygens. I have these 3 oxygens, so I'm going to need 3 waters. That means I need 3 of these H's and 2 Fe's. Alright, got that balanced. Let's do the same type of thing here. Delta S is 1 times our iron oxide and 3 times the hydrogen. That's my products. 2 times my reactants. And now I just throw that into my calculator. So 87.4 plus 3 times 130.6 minus 2 times 27.3 and also minus 3 times 188.7. And we get negative 141.5 joules per mole Kelvin. Alright, so both of these, as they go forward, they lose that randomness or that disorder. Alright, we said we wanted to actually look at how things become spontaneous. Entropy alone doesn't actually tell us if it's spontaneous. Now, back in Chapter 11, we introduced this weird little statement. They said there were 2 things that favored but did not guarantee a spontaneous process. One of them is a decrease of internal energy or an exothermic change. I need to take off this line because that wasn't previous chapter and have a previous chapter. Alright, but basically what we're saying is delta H needs to be a negative value. And the increase of disorder would be, in this case now, a delta S that is positive. Now these are both for the system or the reaction. But those 2 things are the things that favor making a spontaneous reaction. Well, those 2 guys that we introduced in the past, Clausius and Carnot, when they studied this and they realized these guys had to be built off each other, and the later scientists, they actually came up with the second law of thermodynamics. And it actually deals with just the entropy and not the delta H at all. So the heat of the reaction does actually cause an entropy change in the surroundings. And that's a factor into what makes a reaction spontaneous. So the actual second law of thermodynamics talks about the entropy, and it says that over time entropy goes up, or at least it should. Now, more importantly for us, since we're talking about chemical reactions, we're going to say that delta S of the universe needs to be an increase for spontaneous reactions. All right, what does that mean? Well, we know delta S of the universe is a result of delta S of the system and delta S of the surroundings. And here's something we also know. This delta S of the surroundings, we actually said it's derived from the delta H of the system. It is. It is actually equal to the delta H of the system, and you divide it by the temperature to get the units in there. And it does vary with temperature. So the more an exothermic reaction is heated up or cooled down, changes how much the entropy is affected in the surroundings. So there is a temperature dependence. All right, but we got this nice little thing. So we're going to rewrite this equation, and based on just the delta S of the system and the delta H of the system, we are looking for a situation where this is positive, or these two added up together give us a positive value for a reaction to be spontaneous. So what this translates to for us is we actually can use tabulated values from the back of the book to decide if a chemical process is spontaneous. Alright, so let's see what that looks like to actually do it. So we're going to do this particular oxidation. We're going to take FeO, turn it into Fe2O3, and figure out if it's spontaneous. Now, it didn't give us a balanced equation, but I did say that we're oxidizing FeO, and it's going to come into Fe2O3. So I'll back up over here and put a 2 in front of this. That would give me 4 oxygens. I only need 3, so I'm going to have half of an O2. We can do fractions. That's all right in this case. All right, so to figure out if this thing's spontaneous, we need to get our delta S for this reaction and the delta H for this reaction. And we're going to get those from these guys down here. All right, so my product is the Fe2O, and it has a delta S, or an S value of 87.4, and my two reactants, FeO, that is 60.75, and this is 205.2. Before I do the calculation, I'm going to go ahead and write out what I'm going to do with my delta H. So this is negative 824.2, and this is negative 272.0, and oxygen has a heat of formation of 0 because it's in one of those standard states. Alright, so let's do some math. Alright, so 87.4 minus 60.75 and also minus 205.2 divided in half, and we get an S of negative 75.95. Alright, so a decrease in order. I didn't give myself enough room to write the units, but those are joules per gram in Kelvin. So delta H, negative 824.2 minus 2 times negative 272. That's going to be a negative value as well. Alright, so we have an exothermic reaction that loses disorder as it goes forward. Now, we actually earlier said that if we had a decrease of disorder and an exothermic reaction, it was likely to be spontaneous. Well, we can actually modify it. If you had a positive delta S, so a definite increase of entropy, and a negative delta H, an exothermic reaction, it is definitely spontaneous. This is one that's not always spontaneous. Alright, so let's find out if it is spontaneous. Let's figure out what the delta S of the universe would be in this case. Universe. Alright, we're going to have that is equal to the delta S of the system And then to get the delta S of the surroundings, we are going to subtract the delta H divided by the temperature we're at. Now, here's something weird. Now, since I didn't get the units here, it's not obvious, but this was kilojoules. This is joules. So I'm going to turn this value into that kilojoule value into joules when I do this actual calculation. All right. So let's see. I have 75. Let me make that negative. Negative 75.95. And I'm just going to combine these. So positive 280,200 divided by 298. And I get a positive value. It's very small, but it is positive. And that was just 860 or so. What was it? 864. But the number, the value itself, doesn't necessarily matter if I just want to know if it was spontaneous. The fact that it's positive tells me that it is spontaneous. Had it been negative, we would have said it was non-spontaneous. But since this is positive, that is spontaneous. All right, that sure was a lot of work to figure out if something was spontaneous. And something we know that's true in a lot of cases, laboratory conditions typically have 298. It would be nice if these were somehow combined in such a way that you could actually somehow calculate it right off the bat, and if it's at 298, you actually can tell if it's spontaneous or not. Yeah, that's a neat idea. This guy Gibbs did that. So Gibbs actually did a combination of the enthalpy and the entropy and found out that he could make a table, and you could actually use it to calculate if a reaction is spontaneous. And that is also why in the back of your book we have a row that has G's. Now, these units are kilojoules, just like the delta H's. But there is a weird thing here. So exothermic reactions, negative delta H's, were typically found to be spontaneous for a lot of organic style reactions. So Gibbs felt it was beneficial that if a negative thing was something that was likely to be spontaneous, that his Gibbs should be negative as well. So what we have is, we have this weird little dilemma. If you calculate the delta S of the universe, and I'm going to go back to this side, positive is spontaneous. Any positive value is a spontaneous reaction. In Gibbs, delta G is negative when spontaneous. So they're just opposite. Alright, but had I introduced that slide with my rusty nail, we could have actually saved ourselves a lot of time. So our equation we came up with was the two FeOs and half of an O2 gave us an Fe2O3. And look at this. I could have come down here and said, well, I'm going to have just one of these, and I'm going to have two of these, and these are my products. I could just go right across there. And I get, let's see, negative 742.2, my product, minus a negative 255, so plus 2 times 255.2. I didn't have to do anything with the oxygen because it's a 0 in the delta G as well. And I get a negative 231 kilojoules, which really does just mean spontaneous process because the delta G is negative. Alright, so delta G arrow is very versatile and very useful, but it only works if you're right at 298 degrees. If you're any other temperature, this delta G row is totally useless. Now, fortunately, the delta H's and delta S's don't really change with temperature. So we can use these no matter what temperature they are. Well, how are we going to get a delta G at a different temperature? Well, Gibbs figured that out too. Turns out he generated that table by realizing that delta G is just your delta H minus your T delta S. This nice little equation right here. Alright, now, we do have some results we can get from this that actually help us see things from in a different light. Alright, now, when we first introduced the whole idea of that second law of thermodynamics, and first thing, we talked about a spontaneous process as something where we had an exothermic reaction and we had an increase of disorder. They were opposite signs. Well, that actually creates a situation, that's green here. If you have those two things and they're both true, it's spontaneous no matter what you do. There is no change based on temperature. Because if we think about this mathematically, this term is actually going to be negative, and a positive times a negative make this negative. So mathematically, since this has to be a positive value and this has to be a positive value, when this because of how math works, our delta G would always be negative. So delta G is always negative when that happens. Now, if we reverse those two things, so have an endothermic reaction that has a decrease of disorder, we are never spontaneous. But our two catty-corner ones are really interesting. And that's when the sign of the delta S and the delta H are the same. So if delta H is negative, exothermic reaction, but there's a decrease of disorder, it's only spontaneous when this, think about this negative and that negative cancel out. So as the temperature goes up, this term here would get more and more positive. And if it gets more and more positive, it becomes less spontaneous. So we have a situation where it's spontaneous at low temperatures. So when they're both negative in value, spontaneous at low temperatures. Now, if they're both positive, spontaneous at high temperatures. Alright, but we can make a nice little call based on the signs of our delta H's and S's. Matter of fact, back all the way up to where we first did this. When we came up with these values right there and saw that they were negative and negative, we could have actually made the call that said it was this reaction is spontaneous at low temperatures. And we can say that because they're both negatives. Alright, let's do another one of these and actually apply it. Alright, we're going to look at one that I've calculated some delta H's and delta S's. So we're just looking at the values. Alright, but it is just the reaction of SO2 and oxygen to give SO3. And I got the equation right there. And at 298, we have a delta G that's negative. Alright, so that just flat out tells us at 298 degrees Kelvin, this reaction is spontaneous. Alright, but my question isn't, is it spontaneous? It says, is it spontaneous at 900 degrees Celsius? Alright, we do know, because that delta H and that delta S is negative, we know it's spontaneous at low temperatures. And 298 is clearly low enough. Alright, so there is a temperature higher than 298 where it would stop being spontaneous. I just want to know, is it 900 degrees? Alright, so what we're going to do is we're going to calculate our delta G at 900 degrees. And we're going to do that by using Gibbs equation. Delta H minus T delta S. So our delta H is negative 198.4 kilojoules. Our temperature is 900 degrees Celsius, but we want kelvins, so 1173 Kelvin. And our S is negative 187.9 joules. Alright, you see a problem with our units? Yeah, I got kilojoules here, I got joules here. Well, neat thing is, we typically want our delta G in kilojoules, so typically what I always suggest we do is change our S into kilojoules per Kelvin when we write it down. So 0.1879 kilojoules per Kelvin. And now that we have these numbers written down, we're just going to plug this into our calculator and see if we get a spontaneous reaction. So negative 198.4 minus 1173 times negative 0.1879 0.1879. And close those parentheses, and we get a positive value of 22. And kilojoules. Alright, all that tells us, because it's positive, is that it's no longer spontaneous. So the answer to this question is no, it's no longer spontaneous. Alright, what's interesting, we're going to look into this a little bit more here, but they actually do this reaction at 900 degrees. We're going to see that spontaneity doesn't necessarily mean it doesn't occur. It just doesn't go to completion. We're going to see this turns into a two-way arrow, and this positive delta G just means that at 900 degrees Celsius, we're still favoring reactants. But we are going to have an equal mix. Alright, but more importantly, this question was answered with a no, it's not spontaneous. Alright, let's do another one of these. And before we do it, let's actually think about this. Could we actually just predict the temperature that it's spontaneous? We also have to actually answer something else. All right. This said, and we actually can look at this, we said this was a reaction because they're both negative that was spontaneous at low temperatures. Well, what is a low temperature? Because 298 wasn't low enough. 298 is spontaneous. 900 degrees, it's barely non-spontaneous. Positive 22, it's very close to no longer being spontaneous. So how high of a temperature it has to be? All right, let's look at that equation. Delta G equals delta H minus T delta S. All right, the neat thing is we said spontaneous was when delta G was negative. Non-spontaneous was when it's positive. So the point where it transitions from negative to positive is when delta G equals 0. That doesn't look like a 0. 0. Well, this is going to be beneficial because I can rearrange this and solve for temperature. So that equation we just did, rather than actually solve if it was spontaneous at 900, we really could have done this. The temperature where it is spontaneous is just our delta H divided by our delta S. I'm converting our delta S to kilojoules again. And this one went from non-spontaneous to spontaneous. I dropped my negative here. It's okay, I was going to drop them from my calculator. 198.4 divided by 0.1879. This thing becomes spontaneous at, or this thing changes at 10,056 Kelvin. Alright, so since this is negative and negative, any temperature lower, so any from 0 Kelvin to 1056, it is spontaneous. Anything above that is non-spontaneous, which is kind of weird. High temperature in this case is 1,000 degrees Kelvin. That is really hot. And matter of fact, we do actually have some reactions that become spontaneous at any temperature above 4 degrees Kelvin. So, since 4 degrees Kelvin is 4 degrees Kelvin, those are reactions that are pretty much always spontaneous. It's going to be very challenging to get it cold enough that it's below that. Alright, but that would have saved us some time if we'd actually had that nice little relationship, huh? Because 10,056 is definitely a smaller number than the 1173, I think it was. Okay, let's do some more with this. I want to know if this particular reaction is spontaneous or not. And if it is, I want to know if it's always spontaneous, never spontaneous, spontaneous at high temperatures, spontaneous at low temperatures. I want to know everything about this reaction. Alright, right now, I can see from the question that it's a non-spontaneous reaction at with that 8.9 kilojoules positive. Alright, but I want to know if it's always non-spontaneous or just at low temperatures or high temperatures. Alright, so the only way to do that is to get our delta H for each of these reactions. Now I'm going to do this slightly different. Rather than write out that equation like I did there before, where we rewrote these, I'm going to do something that I sometimes do on my answer keys myself. I always did this because, I don't know if you've picked up, I have a bit of dyslexia, and when I write down numbers I tend to write them down wrong. So if I just modify the table into an equation, I typically don't make those mistakes. Alright, but remember how this had to be products minus reactants? And I needed to start over here? Well, I don't necessarily need to. Minus reactants plus the products. Now if I do that, I typically don't make mistakes in my math. So I have 168.6, because those negatives cancel out, minus, because that's going to cancel out, 110.5, and we end up with the delta H of positive 58.1 kilojoules per mole. Alright, then I have negative 93.1 minus 5.686 plus 2 times 33.1 plus 197.5. I get a positive 164, and it will just be 0.9 joules per mole Kelvin. Alright, I got two positive values, so because of the both positive, I know this one is spontaneous at high temperatures. But 298 is not that high, apparently, because it was non-spontaneous at 298. Alright, so let's find out what temperature is our high temperature. And to do that, I'm going to take the delta H, and I'm going to divide it by the delta S. (58) divided by 0.1649. I get a temperature where it changes to non-spontaneous of 352 Kelvin. So I don't want to just give 352. I want to say, in this case, above 352 Kelvin. That's where it will become spontaneous. Alright, what's next? Let's actually figure out... Oh, it's just the same type of question. We want to know if it's spontaneous or not. But I did this one more like I'm going to give you the questions on your test. I gave you every single tabulated value I possibly could. And I gave you the balanced equation. My question is, what are we going to use to figure out if this is spontaneous and the temperature where it's spontaneous? Well, if it just wanted to know if it's spontaneous, it would have given us a temperature. And if that temperature had been 298, we would have used this row right here. But this particular question is wanting to know when it becomes spontaneous and at what temperature. That's totally useless. 298 is one temperature. We need a full range of temperatures. We're going to need our delta H's and our delta S's. Alright, so we're going to do what I did on that previous slide. So these are all 1 times. So products minus the reactants. And our delta H, 634.9 plus 393.51 minus 1220. I get a delta H of negative 191.5. Or I'll go with 6. So negative 191.6 kilojoules per mole. And I have negative 38.1 minus 213.8 plus 110.0, and I get a negative 141.9. Alright, they're both negative, so this is a spontaneous at low temperatures. And it's any temperature lower than, take that number and divide it by negative 0.1419. So any temperature lower than 1350 Kelvin. I'm trying to find you to say spontaneous at low temperatures, and the temperature is that darn high. Alright, this is kind of interesting. Turns out delta G is actually more related to our K. So even though we've been using spontaneous reaction, it's better to say it's spontaneously favoring a direction. What I mean by that, if I have a reaction that actually has a very large negative delta G, it only tells us the degree of how far forward it's going. The larger the delta G is, positive or negative, they talk more about the relationship between our forward and backwards reaction. Well, that's K. Turns out delta G and K are really closely related. So close that they are actually mathematically dependent on one another. Now, interesting thing about this math is our delta G is when we're at delta G naught is when we're at equilibrium. But delta G itself isn't necessarily when we're at equilibrium. Alright, what I mean by that, remember how we were talking in our last couple chapters, our K is when we're at a system in equilibrium and Q is at any other time? Well, there is a delta G that could be calculated when a reaction's not at equilibrium. So, we've actually been calculating what we call delta G oughts, which really are favoring when we're at equilibrium. But when we actually calculate delta G at any given time, if we're not at equilibrium, the delta G could be much, much more challenging or different. Alright, let's see what I mean by that. Let's think about that equation we gave us before, the SO2 and O2 goes to SO3. Now I said back when we first introduced this that we really do this reaction really high temperature. And yet, when we look at the two different temperatures where we might study this, 298 and negative, or 973, we see that 973 is just barely spontaneous, a negative 1212. But it's still spontaneous. But this number here is far, far, far larger. Alright, what we're going to do is calculate what the K would be at these two temperatures and those two delta G's, just so we can see how easy it is to use that relationship. And we are just using this equation at the bottom. So, delta G ought equals negative RT times the natural log of K. Now, the only thing I'm going to do either one of these is specify the temperature we're doing this. So my first one, I'm going to do delta G at 298. And here's something interesting. Delta G's are always kilojoules, but this is your gas constant R that's in joules. So I'm going to write this in joules. And it is negative, equals negative R, and I'll write out the R this time, 8.314 joules per mole Kelvin. And this temperature is 298, and we are going to solve for our K. So, I'm going to ignore the negatives. I'm going to do the 141,600 divided by 8.314, and also divided by 298. And I need to do the inverse natural log. So, inverse natural log. And I get a K of 6.62. what's that, positive 24. Positive 24. Alright, now, the other one's not going to be nearly as large K. See how much smaller the delta G is? But it's still going to be a favorable process. So, what we're going to do is the same type of calculation. 12,120 divided by 8.314. But this time, our temperature is 973. And we're going to do the inverse natural log again. And we get that the K the second time, so K at 973 equals, what's that, 4.47? 4.47. Alright, still favors making products, just not nearly as much. Okay, so we just want to know if it's going to go forward, given a complete set of conditions. Alright. This seems like it could be crazy. It also makes you think you might need to actually use this equation right here. Well, we really don't need to. No need to reinvent the wheel. Let's just do this as an ice table. So, 2 SO2s and an O2, and we have 2 SO3s, and we have initial set of conditions, 0.5, 0.01, and 0.1. I'm just going to plug those in and get a Q. And what kind of Q do I get? 0.1 squared divided by 0.5 squared, and also on the bottom is that 0.01, and we get a Q of 4. Oh, that's nice. It comes out in that nice number. Alright, the question just wants to know if it's going to go forward or not. Well, if we have a Q of 4, and in both cases the K is bigger than 4, whenever Q was smaller than K, we still go forward. So, both proceed forward. Alright, biggest reason we do this isn't because of the spontaneous or not. The spontaneous nature does actually mean that at 973 we will indeed make less of this in the long run. When it's all said and done, the equilibrium will have a smaller mole fraction of the SO3 than it would if we did it at 298. Biggest reason they do it at the high temperature is because even though we get a smaller mole fraction, we get more of it faster because the reaction itself is faster. Alright, let's, yeah, we're not going to need to worry about that one there. Although, actually, let's do it for, heck, both of them. Because this is where we're going to use this wonderful equation. So, if I want to calculate the delta G of a reaction, I'm going to need the delta G ought of that same reaction, and the rest of the equation, excuse me, has R times T times the natural log of Q. Alright, so I got to back up a couple pages. Let's do the first one at 298. So our delta G when we had 298 was negative 141.6. Our R is still the 8.314 joules per mole Kelvin, and our temperature is 298, and remember our Q from the previous slide was just 4. Alright, now biggest reason I want to do this rather than tell you just to plug it in and do it yourself, you're probably going to miss this wonderful thing. Our units change. So I'm going to do this thing over here first. 8.314 times 298 times the natural log of 4 gives me this relatively small number. I'm not adding 3,000 to this because this is in terms of joules. I need to convert it into kilojoules and then add it to my negative 141.6. So my delta G in that case is negative 138.2. Alright, let's see that again with the second one. Our second value, the delta G was 12.12. Where was it? 12.12. And this is still our R. Now this is 973, but this is still the natural log of 4. As long as it's a negative value when we calculate this delta G, we still have a spontaneous reaction. So 8.314 times 973 times the natural log of 4 gives us 11,000. We're going to divide that by 1,000 to turn it into kilojoules. And now we're going to add the negative 1212. We get a negative 0.9 or 0.906. But the fact it's still negative still tells us spontaneous in that forward direction. Alright, let's do a couple more of these. How about if I give you a Ka and I ask you to get a delta G? Well, what throws people off, they see that Ka and they're like, well, what the heck? The equation doesn't show Ka. Well, remember Ka, the A just meant an acid type reaction. It just told us what the reaction was. It's still an equilibrium K. So it turns out we still actually can use that exact same equation. So to get the delta G for this, I really do just take 8.314 times the temperature times the natural log of our K. Now before I enter, do you expect your delta G to be big or small for a weak acid? Think about how that reaction says this favors reactants, right? Because that's a very small K. A reactant favors reactants gives us a positive delta G. Remember this negative here? I didn't put that in my calculator. So this delta G is positive 49.3. And can we use that to predict if a reaction goes forward or not? Well, yeah, we can, but why do it that way? Let's actually calculate our delta G from this and just not try to reinvent anything. We know what our delta G is, we just calculated it. And we're going to do RT times the natural log of Q to this. Well, can't we figure out the Q of an acid? Well, yeah. Our R is still the same R. This is 298. And our Q will be products of a reactants. And any weak acid, bump it into water, the products are H3O plus and A minus. So our H3O plus is 6.0 times 10 to the fourth, negative fourth. Our A minus is the BRO, and the HBRO is 0.20. Let's just plug it in and see what we get. So I'm going to solve my fraction first and then take the natural log of it. So 6 times 10 to the negative fourth times 0.1 divided by 0.2 gives us this. Take the natural log of that 3 to the negative fourth. Then I'm going to multiply this by 298 and by R. And then, remember how this was joules? Let's convert it into kilojoules. and then we'll add that to our delta G. And we get a positive 29.2 kilojoules per mole. Alright. Ooh, that's interesting. Got the last slide, first slide. Alright, that finishes up with this chapter. We got plenty of things to practice on in your textbook, and plenty of things to work on. But mathematically, this is probably some of the easier stuff we've had so far this semester.